So, good morning. Welcome to Maths 206, Abstract Algebra 2. So, today we are going to talk about normal subgroups and quotient group. So, we have been talking about subgroups in the previous lectures. And in this lecture, we are going to look at a special class of subgroup called normal subgroups. So we start with a motivation, an example that motivates the definition of normal subgroup. So you can recall that we look at two examples of subgroup in S3. So S3 is always, the symmetry group is always our place to look for examples. So if you take the group S3 and consider the subgroups H, we have looked at this subgroup before, and the K, which is a subgroup 1, 1, 2, 3, 1, 3, 2. Then the left coset of this subgroup, from what we have learned in our discussion on Lagrange's theorem, we talked about the order of the group being a divisor of the order of subgroup, and then the number of distinct cosets of H in the group G will be the index. So you remember the index of H in G, in this case, because you have 6 elements in the group and 2 elements here, so it will be 6 all over 2, and that will be 3. So meaning we will have 3 distinct left cosets for H, and also 3 distinct right cosets. And the index of K in G will also be 6 all over 3, and that will be 2. So there will be only 2 distinct left cosets and 2 distinct right cosets for this group. This is from what we have learned in the previous discussion. So the left cosets, if I am to list them out, the left coset of the subgroup H, you remember we say H is already one of the left cosets because it will be the one generated by identity or generated by the element 1, 2. You remember these cosets are partition, they form partition of the group. So whenever you are looking for cosets, the given subgroup is already one of the cosets. And then to generate a new coset, you look outside of the subgroup. So we look inside S3, and S3, how many elements are there? 6 of them. 6, 3 factorial. So we have 1, 1, 2, 1, 3, 2, 3. These are the permutations involved included in S3. And then 1, 2, 3. And the last one is 1, 3, 2. These are the 6 elements. So since 1, 2, and 1 have already appeared in my subgroup, being the coset generated by the left coset generated by the identity, and it will still be the same coset generated by 1, 2, then to generate a new coset, you look for an element that is not one of these. So like 1, 3 will generate this coset. And then you multiply this element from the right or from the left by 1, 3. We have done this thing. So this is just to reveal something, to demonstrate the fact that coset, left-right coset may coincide in a given subgroup. And this is what I'm trying to do. So let me do it over here. If you do this multiplication, because this is identity times anything is the element 1, 3. And this is 1 mapping to 2, and 2 is to 2 here. You know, in this notation, when an element is not seen in a cycle, it is fixed. It's mapping to itself. So if you say 1 is mapped to 2, then you now say 2 is mapping to 2 because it's not seen there. Are you following? So 1, you are looking for the image of 1, that is what you will write next. So 1 is mapped to 2 and 2 is mapped to 2, so 2 is the last element here. No, not 2 mapped to 3. 2 is mapping to 2 because it's not there. An element that is not there is mean within that permutation the element is fixed. So these are mappings of 3 elements. So if you want to express 1, 3 as a map, it is 1, 2, 3. So 1 is mapping to 3, and 3 is mapping to 1, and 2 is mapped to 2 because it's fixed there. So 2 is always in the domain, but it's fixed, so we don't write the fixed point. This is what we do. Okay? So you have 1 mapping to 2, and 2 is to 1 here because the last element is mapping to 1, the first element, and 1 is mapped to 3 here. So you can see 2 is mapping to 1, and 1 to 3, so 3 will be the image of 2. And this cycle will close. So this is actually this. We can have a separate class when, if you want me to put you through how you can do this product, to teach you more about permutations and cyclic notations and so on. Okay, but then for the sake of this demonstration, we only need to do this. So this is so this is this. So then to generate the next coset, we still look for an element outside of this, like 2, 3 here. It's not appearing in this coset. It's also not appearing in the first coset. So this will generate a new coset, like 1, 2, 3, and then 1, 2, 2, 3. Is this okay? And this would be equal to, well, you will not have problem here because you understand an identity multiplying anything would give you the thing back. Yes. So, and then when you have 1, 2, so you always look for the image of 1, and then, so you say 1 is mapped to 2, and 2 is mapping to 3, so 1 would map to 3. And then 3 is to 3 here because it's not there, it's not seen, so it's fixed, and 3 is mapped to 2, so 3 to 2. But then all elements have appeared, this cycle must close. So this is what we have. If you now observe, you see that all elements have appeared. You know, 1, 1, 2, 1, 3, 1, 3, 2, 1, 2, 3, 2, 3, and 1, 3, 2. So all the elements of the S3 have appeared. So these are all the left coset. You can do the same for the right coset. The right coset. So right coset of H. So I'll be a little bit faster now. But always the identity is generating the given subgroup. I hope it's okay. So the given subgroup is always one of the cosets. No waste of time, because this will be the coset generated by the identity. It will still be the same coset generated by the element 1, 2, because these things are equivalent classes. And then you look for the coset generated by a different element, say 1, 3. It will be wise to take the same element that you use to generate the left coset. And this would be what? 1, 3, 1, because this time around the product is coming, the element is multiplying from the right, and that is why right coset. So 1, 3, 1, 2. Is that okay? You are multiplying element of H with 1, 3 from the right. And this would be, and you know the way we compose from right to left. So this element acting on, compose with this is an identity mapping. So it will still give you 1, 3. And then you see 1 is mapping to 3, and 3 is to 3 here. So you get 1 to 3. 3 is to 1, 1 to 2. If you still have problem composing permutations, I will teach you how to do it. So this is now 2, 3, mapping the coset generated by 2, 3. So I'm still taking the same element. You see, I'm not paying attention to 1, 3, 2 because it has already appeared here. These things are equivalent classes. So I always emphasize that. And this is now 2, 3, 1. Okay, 2, 3, 1, 2. This is 2. And then you will have, this is 2, 3, because it's multiplying with a identity permutation. And then you can see 2 is mapping to 3, and 3 is to 3 here. So you will definitely have 2 to 3. Well, let me start with 1. Yeah, so I would say 1 is mapping to 1 in this cycle, but here 1 is mapping to 2. And 2 is mapping to 3, and 3 is to 3 here. And the cycle will close. So you can see that this is this is the complete list of right corsets. These are the left corsets. One thing we immediately observe is that this left corset and the right corset, they do not coincide. They only coincide in this particular corset. This is the only corset that coincide with its left. So the left corset generated by identity is still the same right corset generated by the identity. But as for the other corsets, they are different if you look at the element. Yes. So for some subgroups, corsets are not the same. Left and right corset do not coincide. But for other subgroups, we would see that the situation would be different. The left corset will be equal to the right corset. For example, if I'm to list out the left corset of the subgroup K, you remember the subgroup K? It was 1, 1, 2, 3, 1, 3, 2. Do you remember it? And then, so it's already the corset generated by the identity or any of the elements coming from it. Okay? But then to generate a new corset, how many corsets are we expecting here? The index. The index of this subgroup is the order of G divided by order of the subgroup. Remember, it was 6 all over 3. So we had the 2. So therefore, we are expecting 2 corsets. So we just use any element outside of this to generate. So K 1, 2. I can pick 1, 2. I can pick 1, 3 because it's not a member here. So if you multiply identity with 1, 2, or 1, 2, 3 with 1, 2, or 1, 3, 2 with still 1, 2, you get a corset. But this is 1, 2. Well, this is 1 is mapping to 2 and 2 back to 1. 1 will be fixed. So 2 will map to 3. And then I'll have 1, 3. And these are the corsets because the index is 2. So I expect 2 left corsets. And the right corset of K, right corset of K, I will still have 2 of them. Always the subgroup is a corset. So this subgroup, the given subgroup is always both left and right corset. It is the one generated by the identity or any member coming from that subgroup. But then the subgroup, the corset generated by 1, 2, so that will be 1, 2K. And there should be 3 elements inside. And then, but if you remove this list of 3 elements from the group, you have the 1, 2, 1, 3, and 2, 3. So these are the corsets. You can do it if you want. You can do the product, multiplying 1, 2 from the left with this element of the subgroup, and you'll see that the product will still be this. Okay. So, but for this subgroup K, the left corset, every left corset is also a right corset. But here you can see this left corset, 1, 3, 1, 2, 3 is not a right corset here. So it's never a right corset of any kind. And that is all, so this corset is not a right corset. So some subgroup left corset are not equal to right corset. But so for some subgroup, there is no distinction between left and right corset. You can just say corsets because the left corset coincides with the right corset. We will see later on that actually in all situations, if the index of the subgroup is 2, this will always happen. It will always happen, and you can immediately see it. Because if the index is 2, then it means you have 2 left corsets. But the subgroup is already one of the 2 left corsets. So if you divide the element of the subgroup of the group into two and remove half element, which are the element of the subgroup, the rest will constitute of the remaining left coset. It will be the same situation for the right coset. So which means the complement of the subgroup in the group will always be both left and right coset. Meanwhile, the subgroup is always left and right. So there is no distinction between left and right coset for a subgroup of index 2. But then generally, even if the index is 2, this situation can, even if the index is not 2, the same thing can happen, that the left coset equal to the right coset. And such a subgroup will be called normal subgroup. So this kind of subgroup, wherever left coset is equal to the right coset, are called normal subgroups of the group. And they are the ones that are mostly of interest. In fact, we don't need too much these subgroups. It is these ones we need. Because you remember what the subgroup is doing. When you define the congruence modulo relation, it partitions the subgroup, the group into what? Into equivalent classes. And these equivalent classes are the coset. So if you organize this coset as a set, you may want them to form a group, where the elements of the group are cosets. This is a partitioning of the group. Okay? So that organization of the coset into a group will not be possible except when the subgroup is a normal subgroup. That is one of this kind where there is no distinction between left and right coset. So I'm going to formally define what a normal subgroup is, and then we will see, look at some of the properties of this normal subgroup and make progress from that point. So definition now. So let G be a group. Then a subgroup. So to define a normal subgroup, you require a subgroup. It's already a subgroup. So a subgroup N of G is called normal. So a normal subgroup of the group if for all G in G and all N in N, the product G and G inverse is always an element of N. This kind of product is referred to as conjugate of N by G. So if you take any element of this subgroup and any element of the group and multiply the element of the subgroup from left and right by this G and it is inverse, the result will still be in the subgroup. Whenever this happens, then that subgroup is precisely the one of this kind where the normal subgroup, where the cosets coincide. I hope it's okay. So this is what we call normal subgroup. But now if we define for each G in G the subset this one G n G inverse to be the set of all G n G inverse such that N is in N, then our definition, the defining condition for normal subgroup can be presented in this way. Then a N is normal in G if and only if G inverse G and G inverse is equal to N. No, not equal to N, but it is a subset of N. This is what we are saying. It is always included in N. Yeah, okay. So this is it. Okay. So this condition, you can write it more compactly in this way. It doesn't have to be pronounced from the internal view. Externally, you can look at it like this. G and G inverse is contained in G. Then you now say the subgroup is normal. For all G, it should be for all G and G. So for all G and G. For all G and G. So you have reduced the number of quantifiers because you don't have to say for all N. You can just say for every G, G and G inverse, the subset is always contained in N. One can immediately see that, in fact, it is an equality here. In fact, we can immediately prove a lemma. I'll call lemma 3.1. This is the third section of the discussion. So we'll say lemma 3.1. So a subgroup N of a group G is normal if and only if, so if and only if for all G in G, G and G inverse is equal to N. Yeah, so this is it. So we can prove this very easily. Well, if Gn, G inverse equal to N, then certainly Gn G inverse is a subset of N. Yeah, if equality happens, then this set is contained in there, because this is one half of the condition that says equality. I hope it's okay. And so, by the very definition, when this happens, N is normal. So N is normal. It's a normal subgroup. A normal subgroup. If N is a normal subgroup, then we say it is normal in G. This thing I'm using here is as good as saying it's a normal subgroup. So if it is a normal subgroup, then we say it is normal in G. The subgroup is normal in G. So conversely, suppose N is a normal subgroup of G, that is, it is normal in G. It's normal in G. Then, if you say it is normal in G, it means for all G in G, the defining condition, and this is the defining condition. It means for all G in G, G inverse, remember, G inverse is a subset of N. So what remains is to show the reverse inequality, and then equality will happen. And also, for every G, if you take G inverse, let me write it up here. G inverse NG, this G inverse NG, it is the same thing as G inverse N, G inverse inverse, because this is the inverse of the inverse of G. I hope it's okay. So, and already the statement is holding here for all G. So even if you pick the inverse of G, this inclusion will still hold. So if you take the inverse of G, you will still have this. And what is this? This is just saying an element multiplied by n times the inverse of that element. So if you have the element, an element here, G inverse times n times the inverse of this first element over here. This will still be in n. By what? By the very definition of normality. Normality of n. Okay? So thus, if you start with n, it is equal to G inverse n G inverse. But this would be, yeah, I'm writing identity over here, yeah, because this is identity. So n is identity, n times identity, but identity I can write as G inverse. So it means for all G and G, this is happening. And so that is, so I can, by associativity in the group, I can write like G inverse and G inverse. But then this in the bracket is a subset of n. Are you following? So meaning if I remove this smaller set and put the bigger set n, the equality will be an inclusion. It's a subset of G and G inverse by what I have up here. But yet again, G and G inverse is a subset of n again. So this would be content, but I don't have to do it. In fact, you can, if you want, you can do it like that. You can say it is in n. But then since you have this, you have achieved n being in n, you know, equality happens. So implying that G inverse, G and G inverse is equal to n. So not only, so this is actually the claim of the lemma. So not only that if a subgroup is normal, this conjugate will be a subset of n. In fact, equality will happen. It will always be for all G, the conjugate. This is called conjugate. I'm using this terminology, but we are coming to introduce the notion of conjugacy relation, and then you will see. So this is called conjugate. So this conjugate of n by G for every G will always be equal to n. You know, this is a more stronger condition than saying subset. So the lemma is making it more stronger. So this is it. So let me just introduce a notation before we proceed to say that if n is a normal subgroup of G, we write n is normal in G. This is the notation to pronounce that n is normal in G. If you want to say n is a normal subgroup of G, you can just abbreviate it like this. Is this okay now? So n is a normal subgroup of G. Remember the other notation when you say H is a subgroup of G. So H is a subgroup of G. But if you close this like this, then you are now pronouncing that it is normal. So H is a subgroup of G and N is normal in G. It's a normal subgroup of G. Okay. Then we can have a second lemma just to look at some more necessary and sufficient condition for a subgroup to be normal. So you remember what we said, that subgroup for which every left coset is also a right coset are normal. So this should be a defining condition, an equivalent way of defining normality. And this is the content of the lemma. So you can check whether a subgroup is normal just by merely looking at left coset. If they happen to be right cosets, then the subgroup is also normal. So a subgroup So let N be a subgroup of G. Then N is normal in G if and only if every left coset of N is also a right coset of N. So left coset of N in G is also a right coset of N in G. Proof. We can prove this. Well, if M is if N is normal in G, then by lemma 1, we have just proved a lemma 1, 3.1, that for all G in G, what was that? Gn G inverse is equal to N. From this lemma, I can cancel G from the right, so that Gn is equal to Ng. So what is this saying? The left coset generated by G is equal to the right coset generated by G. So that means if N is normal, every left coset will be equal to the right coset. So the left coset generated by G is equal to the right coset generated by G. So, but then the other way around, if we say conversely, if every left coset of N so let me do it. So suppose, make it an assumption like this. Suppose every left coset of N in G is also a right coset. Let G be in an element of G. So, and let G be an element of G. Okay. Then the coset generated by G, the left coset generated by G, well, since G is taken arbitrarily, then we are taking an arbitrary left coset of N in G. So if every left coset is also a right coset, we want to show that N is normal. Okay. Then the left coset Ng of N in G is a right coset. Of N in G. Now the question is, which right coset is it? Which of the right coset of N? Well, since G is an element here, G is contained in the left coset generated by G. So since G is in this coset, and it is a right coset, it means G is in that right coset. Whatever right coset it is, it contains G. Are you following? And because these cosets form a partitioning of the group, so G is also in the right coset of N it generates. So therefore, that right coset, whatever it is, it must be the one generated by G. Are you following? Okay. So since G is an element, we know this. In the coset, it generates, and we say this coset is right coset. It's a right coset, and G we know also belong to the right coset it generates. So you cannot have two distinct right cosets containing what? A particular element. And G is in the right coset of N generated by it. So we must have this NG to still be the right coset generated by G. Yeah, because if you see, if you take it that the right coset, this NG is a different right coset apart from this one, then you are saying G belongs to two different right cosets, but that is not possible because this right coset is a partitioning of the group. Okay? But once this happens, what do you have? But then you have the desired result because you just cancel G from here. So what you have is NG, G inverse is equal to N. So that by the lemma, N is, by lemma 3.1, N is normal in G. And this is what we wanted to prove. So actually, a subgroup is normal if and only if for every G, NG equal to Gn. So every left coset is also a right coset. And it will be the same right coset as the one generated by the generator of the original left coset. So this is always the case for subgroup. So actually that property we identify for the subgroup K was a defining property or a characterization of the normal subgroups. Well, so let us make some progress. So example. So we have already seen that subgroup. One example is already before us because we have seen that the subgroup K, which was 1, 1, 2, 3, 1, 3, 2, is a normal subgroup. Normal subgroup of what? Of the group S3. The second example I will give you is that if G is abelian, remember abelian group? Commutative group. The binary operation is commutative. Then every subgroup of G, every subgroup H or N, H of G is normal. Every subgroup is normal in the case of abelian group. Why is this so? You know, if you are talking about abelian group, product is commutative. So automatically, always for every G, you can always have GH to be equal to HG. This is always the case because of normality. You know what? You remember what this is? This is a set of all HG, such that H is in H, and this will be the set of all GH, such that H is in H. But then GH equal to HG for normal subgroup. So these things are the same. So every subgroup of a normal subgroup is always normal. Are you following? Like the group of integer under addition. We are talking about group of integers under addition. For instance, in the group of integers under addition, so z plus, if you take h to be the subgroup, all multiples of 3, any one of them you take, is a normal subgroup. So it is a normal subgroup of z, whatever subgroup you take, because the group is already abelian. I hope it's okay. The group of real numbers, non-zero real numbers under multiplication, all the subgroups will be abelian and so on and so forth. But we have seen a non-abelian subgroup of the group of S3, like that group H, that subgroup H. You remember it in our first, in the example we consider. Okay? So, but then I made some remark about this subgroup, because what was the index of this subgroup? This subgroup is of order 3, and the group is of order 6. The index is 6 all over 3, 2. So it is a subgroup of index 2 and happen to be normal. This property is general with all subgroup of index 2. So once a subgroup is of index 2, it will always be normal. We can present that as a result. So if H is a subgroup of G group, a group with the index of H in G equal to 2, then H is normal. It's normal in G. Well, I will leave it as an exercise. It's an easy exercise here. Yes. It's not difficult to see, because you have, if you say index is 2, then you have 2 cosets, 2 left cosets. So there will be only 2 left cosets, H1 and H2. And there will be 2 right cosets as well. And the right coset, you can call them well, what you need to understand is that the first of the left coset must be H. I hope it's okay. And then the other one will be the complement of H. So actually, the other coset will definitely be G minus H. Are you following? And if you come to list the right coset, the first in the list is the subgroup itself. And the second in the list will be the rest, because the number is always 2. And if you unite, you must get the group. So it must be G by H also. G minus H, set minus. So while every left coset is also a right coset, because the index is 2. I hope it's okay. So subgroup of index 2 are normal in a group. So this is another way of seeing that. But you know, this result is not conversely. We are not saying every normal subgroup must be of index 2. But like for example here, we have a normal subgroup, but the index is what? I don't know that you can, even though it's an infinite situation, but the index is 3, because you are talking about modulo 3. You start grouping, you will have H plus 0 as one of the coset, and H plus 1 as the other coset, and H plus 2 as the third coset. There are only 3 cosets here. So the index is 3. So it's not necessary that a normal subgroup will have index 2, but whenever the index is 2, the subgroup must be normal. This is what we are seeing here. So, well, the main thing about normal subgroup is what I'm going to say now. That is, because if we are talking about normal subgroup, so HG is always equal to GH. So there is no distinction between left-right coset. So if I am speaking of the normal subgroup, I can just say cosets without having to say left or right. I don't need to mind whether I'm dealing with the left or right coset. So once you say coset, there's no difference between left and right, because every left is also a right, vice versa. So if you have the cosets of a subgroup, can you organize them into a group? That is, you take the collection of all cosets, it's a partitioning of the group. Can you organize them into a group? You know, this will not be possible except when the coset is the subgroup is a normal subgroup. If the subgroup is not a normal subgroup, you will not be able to have a way of multiplying cosets to still get another coset. So you can still recall we define products that for two subsets A and B of G a group. So let me mention it. Of a group G, AB, we define product like this: AB to be A times B, such that A is in A and B is what? In B. Okay? We can do the same with the cosets. We can do the same with coset. So if N is a normal subgroup of a group G, then given any two cosets, we can multiply them. Given any two cosets, NG and NH. But by now we have no need to take it. So it's left and right are equal. I have mentioned it. So no need to say whether left, right. So given any two cosets, I am adopting the left coset of N in G. We can multiply. So we have that product. So NG and NH. But you know, if you do this product, what you are saying is multiplying element wise. So you take an element of this coset and multiply with element of this coset, as if you are looking at A here as NG and B as NH. But because of the fact that these things are cosets, when you do that product, the output, it will eventually come out as a left coset, because you can do associativity. So you can write it as NGNH. Is that okay? Yeah. But then this left coset or right coset. So what I have is NGH. But then that is NN GH, if you do away with the brackets. But what is NN? Because N is a subgroup. So please note that whenever H is a subgroup, H times H will always be equal to H. Okay? Because H is closed. If I take any H1 and H2 from here, the result is still in H. So H1 is a subset of H. HH is a subset of H. And if you take any element H, it is the same thing as H times identity. And so it's a member inside HH. So the other inclusion is also holding. So you always have equality. HH is equal to H for any subgroup. So therefore NN will still be N, GH. I hope it's okay. So if you multiply two cosets, you still get a coset. The product of two left coset is still giving me left coset. This situation will still happen even with the right coset. If I multiply two right coset, I will still get two right coset. In fact, this thing, you see, I had to swap the position of N and G here. So I was using the fact that the Gn is equal to what? Ng. I was using the fact that Gn is equal to Ng. That is left coset equal to right coset. And so we were assuming here at this point that the subgroup is normal. So this situation will not always be possible except when the subgroup is normal. In other words, what I'm saying is that the product, so we can present this as a result, lemma 3.4, okay? That, so, okay then, so we can now organize as a lemma the fact that whenever this happens, then the subgroup must be normal. And if it is normal, this will happen. So actually, a subgroup, this is still another characterization of a subgroup because it uses precisely the fact that left coset are equal to right coset. So we would say that a subgroup N of a group G is normal if and only if the product of any two left cosets of N G is also a left coset, of N in G. So this is the result. Well, we have already proved the first part. That is, this is the proof of the, if N is normal, then I can do the multiplication like this. That is, I can use the fact, if it is normal, then Gn equal to Ng, then I do it and get that the product of two left cosets is equal to a left coset. But then the converse is what is left to be proved. So if N is normal in G, then we have seen that for all G and H in G, if you multiply the left coset generated by G and the left coset generated by H is equal to the left coset generated by the product. So product of two left cosets is a left coset. So if N is normal, then the product of any two left coset is also a left coset. So we have proved that. This is what we have demonstrated. And it uses the fact that N is normal. That is where we get to replace left coset with the right coset, or right coset with the left coset. Conversely, so if we suppose the product of any two left coset is also a right coset, then what happens? So if the product of any two left coset of N in G is also a left coset, a left coset, then so we are saying that for any, so we say suppose the product of any two left coset is also a left coset. Let G and H be element in the group, then by our assumption, NG composite NH is a left coset. But which left coset will it be? So it's a left coset. Which left coset must it be? If it is a left coset, we want to know which left coset. And since so I can see that G, because product here, you see element here are N1G, N2G, where N1 and N2 are coming from where? So if you pick any element from here, it is of the form N1G times what? N2H, not G, sorry, times N2H. It is element from here, you are multiplying with element from here. An element in here are N1G. An element in here are of the form N2G. Are you following? So since I can write GH as identity times G, composite identity times H, this product is in NG, NH for sure, because identity is a member in N. Are you following? So that means the left coset, this left coset contains this element. And any member, you can pick any member from a left coset and use it as the class representative. So since this happened, so we have that NG times NH to be equal to NGH. So it must be the left coset generated by GH. Is that okay? All right. And so now, for all N, for all G in G, and all N in N. So with this, we now see that G N G inverse can be written as identity G N G inverse. This particular element is in the product of two cosets NG composite NG inverse. Yeah, but then when you multiply, it results to a left coset generated by the product of the individual generators. So this is actually N G G inverse. So what is this? This is N. So you get G N G inverse to be in N. So therefore, N is what? It's normal in G. So with this, you get N to be normal in G. So that is it. Okay. So this is this one. So, but what have we achieved? We have gotten yet again another characterization, which means of normal subgroup. Whenever you see that the product of two left cosets is also a left coset, then that subgroup is normal. And since this condition, this statement is biconditional, if N is normal, this will happen. And whenever this happens, that product of two left cosets is still a left coset, N will be normal. So only for normal subgroup you can organize cosets or left cosets into a group. So this is what we will do now, leading to what we call quotient group. Do you still have more time? We spent up to an hour.
Yes.
Okay, maybe we stop at this point so that in the next class we'll start talking about quotient group. So I will define quotient group, then we will prove that this composition is well defined in the set of all left cosets of a normal subgroup, and then we will now introduce the notion of group homomorphism. Thank you very much.